Hello math folk, it's Mr. Ray with our next lesson in advanced functions. We're working in the polynomial functions units, and recently we've learned how to factor polynomial equations and expressions. From that we were able to use that skill to solve polynomial equations, and we're moving to the next step, which is solving polynomial inequalities. So the difference between equations and inequalities is the sign in the middle of the two expressions. So equations always has an equal sign, but an inequality, you can have one of four signs: greater than, less than or equal to, greater than, equal to. So you've got these four possible signs in the middle, where equations, it was always just an equal sign. When you're solving equations, polynomial equations, you remember most of the time we just had a finite number of discrete answers, meaning something like you might have the solution could be x is -2, 3, or 10. With what you're going to see with inequalities is there's going to be a range of solutions. Okay, so that's going to make it a little bit more difficult, but not a whole lot. So, all right. Now, when we're solving inequalities algebraically, this is an important thing here. The same rules apply as when you're solving equations. For example, you want to treat both sides like a scale. Do the same thing to both sides. Add something, multiply something. But there's a big difference, one major difference with inequalities. If you multiply both sides by a positive number or divide by positive numbers, that's okay. But if you multiply or divide both sides of an inequality by a negative number, then what happens is you can still do it, but you have to change the direction of the sign. So if it's a greater than sign initially and you multiply by -2, you have to change the sign to less than. Okay. Now there's a couple of, once you get into polynomials that are higher than linear, like quadratic or higher, there's two ways you can do it, two major ways. One is when you look at all the possible cases, and the second one is using intervals and then testing values for each interval. The method I vastly prefer is the second one, and that's what I'll be doing for these examples that are quadratic or higher inequalities. You might see in textbooks or on the internet, what they do is they have a table of all possible signs of every factor and then what comes out of that. We kind of do that same thing with intervals, but to me it's much more logical and understandable. Okay, so the method you choose is up to you. If you prefer to consider all cases, then and you get the right answers, well, that's fine. So go ahead and do that. But from my experience with students, most students embrace the interval method because it makes more sense to them. Okay, so we're going to start off with some linear inequalities. So we're going to solve these, and then we're going to show the solution on a number line because, again, it's a range of values. So x minus 8 is greater than 3. That's what we're starting with. So, if we were solving this, we'd just add 8 to both. If we were solving an equation like this with an equal sign, we just add 8 to both sides. Well, we do the same thing here. We're going to add 8 to both sides, and I'll just put what we're doing here. So if we add 8 to both sides, we get x is greater than or equal to 11. Okay, and then so that's an infinite number of solutions. Even if you just looked at integers, but with real numbers, of course, it's going to be infinite number. So if I was looking at a number line for the solution, so the number line, you'll put a horizontal line with two arrows going to positive and negative infinity. And then what we're going to do is the key number here is 11. So I'm just going to put that in the middle. Okay, so we'll say 11 is right there. Now, the key, one of the things we have to look at first before we actually pencil that dot in is this is greater than or equal to 11. So you can tell from the solution here that the solution includes 11. Okay, so 11 is part of the solution, so we call it closed circle. Okay, and it's greater than or equal to 11, so that means everything to the right of 11 and including 11 is part of the solution. So I'll shade that in, make the arrow a little darker, and that's basically showing the solution on the number line. And if I want to put it in interval notation as well, below I would say x is an element of, and then I'm going to put the interval where the solution is. So since it includes 11, that's the lower end of the interval, I'm going to put a square bracket to the left. That means it's including 11 because of the closed circle. And the upper end is positive infinity. You can either just put infinity, or I just like to put the plus sign to make sure it's clear. And then with infinities, we always put a rounded bracket at the end. Okay, so that would be the solution on a number line and in interval notation. Okay, so we have another one here. -4 minus 2x is less than 12. So again, we're going to try to do this algebraically. So the first thing I want to do is clear up that -4. So I'm going to add 4 to both sides. When I do that, it clears off the -4. The 12 bumps up to 16. So I have -2x that's left over and a 16 here. And this is where this rule changes. So if I want to clean out the -2 coefficient here, I'm going to have to divide by -2. So we still do that, but when I do that, I'm going to have to flip the direction of the inequality sign. So divide by -2, that changes to x, positive x. This changes to -8, and the less than sign changes to greater than. Okay, so there's our solution. So in terms of a number line, again, horizontal line, arrows. The key number here, and there's only one, and that's -8. So I'll put my -8 here. Now this time, the solution does not include -8, whereas the previous one included 11. When it includes the number, you put the closed circle. When it doesn't include the number, you put an open circle. So you can exaggerate a bit, make the circle a bit bigger, so it's clear that it's an open circle. And it's greater than -8, so it's to the right. So again, I'm going to put my solid line going. Everything above -8 is part of the solution. And when I put this in interval notation, so x is an element of, and the interval starts at -8, but it does not include -8, so I put a round bracket, and then the upper end is positive infinity, and we always put round bracket for infinities, and there's our solution. So that's a key point. Anytime you multiply or divide by a negative number, you change the direction of the side of the sign. If it doesn't matter what you add or subtract, could be positive, negative, that doesn't make any difference, but it's the multiplying or dividing by a negative number that changes the direction. Multiplying or dividing by a positive number has no effect on the direction. Okay, this one here is kind of an odd looking creature. It's actually got 3 sides to it. So it's got a middle part and a left part, left side and a right side. So you probably never see anything like this because equations couldn't have 2 equal signs. So what we're going to do is we're focusing in the middle part. That's where the x is. Okay, so what we want to do is we want to change this to an x, but every time we do something in the middle, we also have to do it to all three sides, the left, the center, and the right side. So the first thing I want to do I keep wanting to say both sides, it's like all three sides. We're going to add 1, and that will take care of the negative 1. So when I add 1 to negative 5, I get negative 4. Add 1 there, we're left with 2x. And if I add 1 to 13, I get 14. Okay, and now to change the 2x to x, I'm going to divide all three sides by 2. So divide by 2. This time we're dividing by positive, so it's not going to affect the direction of the sign. So that's going to be negative 2 is less than x, which is less than 7. Okay, so basically the solution is going to lie between these 2 points, these 2 values. Okay, so this time I actually have 2 important values on the number line. I have negative 2. Now the scale here doesn't matter to me. You can put these numbers anywhere you want as long as the one on the right is higher than the one on the left. So I'll put my 7 over here. Okay, now this is saying that x can be any number between negative 2 and positive 7, but it doesn't include those numbers because it doesn't have the equals. So these will be open circle, and then I'm going to shade in everything between negative 2 and 7. Okay, so this is the first one we've seen with a beginning and an end in the interval for the solution. The other 2 went on forever in some direction. So if I'm going to put my interval notation for this solution, I'm going to start at negative 2 and at 7, and in both cases it doesn't include the numbers, so that means round brackets. And there's my interval notation. Okay, so now what we're going to do is move on to some higher degree polynomials, some quadratics, and a couple of cubics here. One quadratic and a couple of cubics. So first one we have, you can see it's already been factored for us, which is nice. And the other nice thing is we've got a 0 on one side of the inequality. And that's an important thing to mention. Anytime we have an inequality, we're going to have to, same thing as what we did for solving polynomial equations, we want to get a 0 on this side. So we're kind of lucky there's a 0 there. If this had been like a 2, it would be a lot of work because we basically have to expand this, subtract the 2 from both sides, and then try to factor again. So in this case, we don't have to do anything. So if that was solving a polynomial, I would be finding the zeros. So we actually need to find the zeros first. Okay, it's not the final answer. So the zeros would be negative 3 from the first factor and 3/2 or 1.5. So those two values of x will make this inequality 0. You'll have a 0 on the left side, and since that's an equal 0, these are part of the solution. So what we do from this point, because it's a quadratic or higher, we don't actually know the number yet, and we're not going to solve this algebraically other than factoring it. Okay, so let me just move this down a little bit, give myself some more room. Okay, so same number line. This time I've got two values that are important. So I have a negative 3 and I have a 1.5, and again the scale, scale is no big deal. I would try to separate them just so you can, some cases you're going to have 3 or maybe 4 values, 4 zeros that you'll have to put in. So that becomes more important for the scale. I mean, you don't want to put, you want to put the numbers relative where they are on the number scale, but You definitely don't have to take out a ruler and make sure they're to scale, okay, for what we're doing. Okay, so what we're going to do here is we know that -3 and 1.5 are part of the solution. Okay, so that what we just put there is true. The closed circle means that's part of the solution, but we don't know, is this part to the left of -3, is that part of the solution? Is between them part of the solution? To the right of 1.5, is that part of the solution? So this is the technique we're going to do, and hopefully you'll find it easy to use. So what we do for each interval, so since we've got two zeros, we have 3 intervals to work with. This interval, this interval, this interval. So for each of the 3 intervals, I'm going to pick a test value that lies within that interval. So you have, in most cases, you have quite a few options. There's a few good choices. For example, if I want to pick a number between -3 and 1.5, I'm definitely picking 0. So if you want to do this, just to kind of separate the intervals, because I'm going to put some writing in here. So this interval, my test value that I'm going to pick is x equals 0. Okay, if I want to pick a value above 1.5, well, probably my choice would be x equals 2. That's definitely above 1.5, but I don't want to make it too hard because I'm actually going to have to use these numbers for calculations. And then if I want something, a test value less than -3, well, I'm picking -4. So I picked my 3 test values, and now what we do, we actually take our test value. So I'm actually going to start with this middle interval just because it's easier to work with. I'm going to plug that test value x equals 0 into each of these factors. Now, I don't really care the value. All I care about is the sign. Okay, so when I plug x equals 0 there, the first factor is positive. So I put a little plus sign. So I don't care that it's plus +3, I just care that it's positive. And if I put a 0 in to the second factor, that's 2 times 0 minus 3. So I get -3, so that means negative. Okay, so I don't really care about the value at x equals 0. I care about what sign does the result always become when it's between these two values. So if I multiply a positive and a negative, that means I'm going to get a negative overall result. So in this interval, I'll put a little bit bigger, like a negative sign in brackets, because I know that the result, the y value, if I made this into a function, would be negative. So basically, if I was thinking graphically what this looks like, I know that I have a 0 here and here. I know that the y values are negative, so I actually know that the graph will come down below here. So I do the same approach for the other intervals. I plug in x equals 2, and you can see I'm going to get a positive value for the first factor. I'm going to get 2 times 2, 4 minus 3 is 1, so that's also positive. So positive times positive is positive. Okay, and then finally -4, if I plug that in, you can see pretty quickly I'm going to get both of them being negative. Okay, and if I multiply 2 negatives, I get overall positive value. So if I'm looking graphically, I could see that the graph would come down there if I'm just looking at that f of x equals x plus 3 times 2x minus 3. So the graph comes down there. I don't have to think graphically, but sometimes that helps. That's what those signs represent, that the y values in this interval are negative, the y values here are positive, and they're positive here as well. So now we go back to, well, what was I looking for again? I want the result of this inequality. I want it to be greater than or equal to 0, which means positive. So now I go back, I hunt down my positive intervals, and I shade them in because that interval will give me the result I want, and also this interval. Okay. Now, if I plugged in any number between -3 and 1.5, this would not be true. But every other number outside of that interval would work. So so that's basically a number line approach, but we're working with each interval. We pick any test value for x in each of the intervals, plug it into the factors, see what the sign of each factor is, and then overall what's the sign of that interval. Okay, so now I can take my shaded areas, turn that into interval notation. So my interval will be x is an element of, so the first interval goes from negative infinity, which we always start with a round bracket, and it ends at -3, and it includes -3, so that means square bracket. Now in this case, unlike the previous example, we actually have two intervals that are part of the solution. So the way we join that with interval notation is with a U symbol for union. You basically read this as or, so it's this interval or it's this interval. You can't say this interval and this interval because that implies the value of x has to be in this interval and also this interval, which wouldn't be possible. Okay, so it's the or. If you're reading this, it's or the word union. Okay, so the second interval starts at 1.5 and it includes 1.5, so square bracket, and goes to positive infinity, round bracket. Okay, so that's how you do it with using selecting intervals and test values for the intervals with using a number line. Okay, so the number line I find very, very useful, and you can, like I did earlier, you can kind of see what the graph might look like based on positive, 0, negative, 0, positive. So it's basically going to be a quadratic that opens up. Okay, here's our next example. You can see it's a cubic, so a little higher degree of difficulty. So you can see it's already set up. It's an inequality, and we have 0 on one side, so that's good news. However, it's not factored, so that means more work. Okay, so what we're going to do here, the first thing I noticed, I can see I can actually common factor a 2 or a -2 out of here, and since the leading term is negative, I'd like to common factor a -2 outside. So I'm going to be left with x cubed plus 3x squared minus 6x minus 8 bracket, and I'm only common factoring out -2. I'm not multiplying or dividing, so don't think you have to switch the sign when you common factor. Okay, so basically these equations are the same, and now in order to get rid of the -2, basically I'm going to divide both sides of the inequality by -2, and that should send up a flag. Okay, that's the situation. If I divide both sides by -2, I'm going to change the direction of the inequality. So when I do that, I'm changing it to that. So the equal sign stays there, but it changes from less than or equal to greater than or equal to. Okay. All right. I'm going to leave out a couple steps here. Basically the factor theorem and the division parts. It just take up a lot more room, but let's just assume we did this and we found on our step that P of -1 we tested, and we found out that when we plug in x equals -1 into here, we get 0. Okay, so that tells us therefore x plus 1 is a factor. So that's the stuff we did in the last couple of lessons. And then in order to figure out, so this left side changes to x plus 1, and I'm going to assume we did our division on a sidebar or a separate piece of paper. If you divide x plus 1 from this cubic, you're going to get x squared plus 2x minus 8. as the quotient. Inequality sign is unaffected, and we can see that's a pretty straightforward simple trinomial factoring. So that's x plus 1, x plus 4, and x minus 2 is greater than or equal to 0. So this time we actually have 3 zeros. So I'm going to create my number line again, give myself more room. Okay, so this is what I was talking about with the scale. So now it's a little bit more important. So we've got zeros at -4, -1, and 2. So I'm going to put my -4 here, -1 here, and 2 over here. Actually, they're about the same distance apart, so that's actually pretty good. Now, before I darken these circles, I have to figure out, these zeros, are they part of the solution or not? And we can tell very quickly because there's an equal sign there. So this can be 0, so that means all 4 of these zeros are part of the solution. Okay, and now we can split up our entire interval into 1, 2, 3, 4 intervals, and now we're going to pick our values. So something less than -4, I'm going to pick -5. Something between -4 and -1, I'm going to pick -2. Between -1 and 2, always pick 0. And greater than 2, I'm going to pick 3. So those are my 4 intervals. I picked a test value for each of them. Now I plug them in. Now this time I've got 3 factors, so I'm going to have 3 signs. Okay, so let's just go left to right this time. So if it's -5 for x, I'm going to get negative, negative, negative. So this time I'll just put the signs, and 3 negatives multiplying together give me a negative. So overall, this leftmost interval is going to be negative all the time. If I plug -2 in, this time I'm going to get negative, positive, negative. So negative, positive, negative, and that's going to result in positive overall because the 2 negatives turn to positive. And then 0 is going to be positive, positive, negative, which overall would be negative. And then 3 would be positive, 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 which overall is positive. And after you've done a few of these, you should probably notice that usually it alternates between negative and positive, right? And that happens most of the time, but not all the time. You're going to have some situations where you're going to have 2 neighboring intervals that actually do have the same sign. So be careful with the signs. Don't always assume that it alternates, even though most of the time it does. Okay, so now we've got our signs of our intervals, and now we go back to, well, what are we looking for, positive values or negative? And you can tell because it's greater than 0, we're looking for positive. So that means I want this interval as part of the solution, and also this interval as part of the solution. So if I make my interval notation for my answer, x is an element, and this time I'm going from -4 to -1, and I'm including both, as we talked about earlier, because of the equal sign in the inequality. Okay, so that's the first interval that's going to be part of the solution. The second one, so I'm going to join that with a union symbol, which is OR. It starts at 2, includes 2, so I'll put the square bracket, and goes to positive infinity, and the round bracket goes there. So that's my solution there. So hopefully you're seeing how this works. Hopefully it's something that makes sense to you, and you could try it yourself. Okay, the third one here, the last one we're going to do in this question. This one's quite a bit different. You can see I basically got a cubic being greater than a quadratic. So what we want to do is, remember the rule, we had to have one side with a 0 for the inequality, just like equations. So I'm actually going to subtract each of these terms, 3 terms from both sides. So I'm going to get the x cubed, and then I'm going to subtract 2x squared. So I'm going to get a minus 4x squared. I'm going to subtract 14x from 5x. So I get minus 9x. I'm going to add 16 to both sides. So I get a plus 36. Greater than, and since I've removed all those, I now have what I want. Okay. So now what we have to do is find the zeros by either factoring, or in this case, remember when you have four terms, sometimes the if we group the first 2 terms and last 2 terms and then factor, sometimes that works, and you can kind of see there's a chance of that, because I'm going to have it like an x minus 4 to there, and if I divide that by -9, I'm going to have a x minus 4 there. So let's try it and see if it works, because if it does, it'll save a lot of work. So if I group them first, x cubed minus 4x squared minus 9x, don't forget I got to change the sign there to minus 36. Okay, so this technique works for inequalities just like it did for equations, and just like it did for expressions. So if I factor an x squared out of there, I'm going to have an x minus 4. And if I factor a 9 out of there, I'll have an x minus 4. And that's good news. That the fact that those 2 binomials are the same means they're a common factor. So I'll take that out, left with x squared minus 9. And luckily, that's a difference of squares, so we can factor that very quickly. That's an x minus 3, x plus 3, greater than 0. Okay, so that was a lot better than finding test values, candidates, and using factor theorem to find which ones are actually zeros, and then dividing. So that saved a lot of work. I didn't actually leave out any steps like I did up here, where I didn't show this work, and I certainly didn't show the division. So if you can do this method, factor by grouping, it's a time saver for sure. So now we know for this solution, we've got 3 zeros. We got -3, 3, and 4. So when I do my number line, so I got, -3, 3, and 4. So I've got -3 down here. I've got 3 up here, and 4 a little closer. It doesn't have to be exact like I've been saying. Now, here we have to be careful, because this time it's not greater than or equal to. So the zeros, which are these 3 values, are not part of the solution, because the solution is when the value has to be greater than 0. So this is where you're going to put your closed circles. Okay, sorry, hopefully you saw that. So now you can see if we divide this into intervals, you can see we got 1, 2, 3, 4 intervals. Let's do some test values. So, you can kind of see the pattern now. X equals -4 is my test for there. X equals 0 is my test value here. This one's a little more restrictive, between 3 and 4, so this time we have to pick a decimal, so 3.5. It's not going to be as hard as it looks though. And then x equals 5 for this final interval. And now we're going to plug these values into each of the 3 factors and get the sign of the interval overall. So -4 means that's negative, that's negative, that's negative. So 3 negatives means overall it's going to be negative. Okay, 0, plug in 0, I get negative, negative, positive, which means overall it's going to be positive. If I plug 3.5 in, that is negative. that is positive, and that is positive. So negative, positive, positive. Okay, and overall that's going to be negative. And then finally 5, you can see that all 3 would be positive. So overall it's positive. And that's because we're multiplying all these factors. Okay, so now we go back to our question to see, are we looking for negative or positive intervals? We're looking for positive because of the direction here. So I'm going to put my first interval is the negative interval here. Sorry, I'm looking for positive. So it's the first positive interval. And don't shade in those circles because they're not part of the solution. And then this final interval here is also part of the solution. So when we go back and do our interval notation, first interval goes from -3 to +3. And this time we don't include those zeros. So we put round brackets. And then we join that to another interval. So that interval is 4 to +infinity. And because we don't include the 4, it's a round bracket as well. Okay, so hopefully that makes sense. I mean, we've done three different ones where, one was already factored for us. So we got the zeros very quickly, did our interval testing, and then came up with our number line solution and translated that to interval notation. This one here, we kind of skipped a couple steps. We factored out -2, changed this direction. We found a value of x that created a 0. So then we knew a factor, x plus 1. We divided it out from the original equation here. And then we're able to factor that as well. Found our 3 zeros. The rest was the same as before. Test each interval and then come up with our intervals notation solution. And then this one here, we used the factor by grouping to find the factors, which was a nice quick method of doing it, and found our 3 zeros, set up test values. This time, remember, the zeros aren't part of the solution, so they're open circle, tested our intervals, found the ones that are positive, and then translated that into interval notation. Okay, hopefully that makes sense. Now this is a different animal. This is kind of working backwards. So this time they're actually giving us the solution and they want us to create a possible inequality. Now, if they gave us this, I mean, there's an infinite number of inequalities that could create this as a solution. So that's why they said possible. But they're all going to have something in common. So now the first thing I'm going to look at is go through the key numbers here. Obviously, negative infinity is not going to be important because it's just starting from the far left end. But I've got a -4. So I'm just going to write these values. Now the next one I have is also -4. And then I have a 1. And then a 2 and a 6. Okay. Now the -4 is intriguing. So why wouldn't they just do the interval all the way from negative infinity to 1? Okay. And the key here is the round brackets. So that it says the first interval that works is negative infinity to -4, but it doesn't include -4. Okay, because of the round brackets. The next interval is from -4 to +1, but it doesn't include -4 or -1. Okay, so basically it's everything from negative infinity to 1, but except for 4. So, and then these other ones are fairly straightforward, 1, 2, and 6. They shouldn't be a problem. So what I'm going to do is start with the number line and put in my key values. So I've got a -4, I've got a 1, I've got a 2, and I've got a 6. Okay. So the first interval if I'm putting my solution here to basically translate this to the number line solution, it starts at negative infinity, goes to negative 4, but it doesn't include negative 4. So basically I've got that, and the next interval that's part of the solution is negative 4 to 1, not including either one. So that's interesting. And then the next one, it skips. So it skips to 2 and goes up to 6, not including either one. So there's my number line solution. I don't want to make that look like it's closed. Okay, so I have to create an inequality that has this as a solution. Okay. Now, one way you can do this is come up with a graph that works for this. So I'm thinking, well, what if my graph or my function comes down here and it hits negative 4 as a 0 and then comes back up? Now, the reason why I'm bouncing like that is because I'm thinking ahead a bit. I know that both of these are solutions. So both of these sides, the function has to be positive, or both sides have to be negative. So it could be this as well. Okay, I have to decide, do I want my solution to be less than 0 or greater than 0? So, and I'll show you, maybe an alternate answer. So basically, I kind of know this is going to come back. It's not going to keep going up forever. It's going to come back down. It's going to hit negative 1. That's where 0 is. But this time you can see I have a change in, so this is part of my solution. This is not. So if I'm kind of assuming for the time being that I want my solution to be greater than 0, so that means it's going to dip below 0, come back up, go above 0 between 2 and 6, and then back down here. Okay, so that seems to work. So if I'm basically saying this function has to be greater than 0, this would be the solution that works. So the first thing, I have to start creating my equation. Okay, so the first thing I'm going to start with is my zeros. Okay, so I have a 0 at x minus 4, so that means my factor would be x plus 4. Okay, but the interesting thing about about that 0 is it bounces, and you remember if it bounces, it has to have factor has to have an even order. So at minimum, it would have to be a 2 there. And that's where you could have infinite solutions. I could have an exact same function or inequality and change that to a 4, and it would be the exact same. Of course, the graph would look different, but the solution would be the same. All right, the next 0 would be at x minus 1 as a factor because 0 there. The next 0 is at 2, so that would be x minus 2. And then the next 0 would be x minus 6. Okay, now the only thing we have to concern ourselves now is this is giving us the zeros, but it's not really giving us the end behavior. So right now here, the end behavior, so this would be degree 2, 3, 4, 5. This is degree 5. So it's either going this way or this way, depending on the leading coefficient. And we want it to be this one, right? So this end behavior, I've got the right degree. It's an odd degree, but the leading coefficient, the way I've written it here, would be positive. So that would not be that graph, it would be this graph. So to fix this, all I have to do is put like a negative value out front here. Okay, and I could do like a negative 2. Maybe I'll do that, put a negative 2 out here, and this flip-flops the end behavior from what I'd written previously to duplicate this. Now, in order to make the inequality now, that's just the graph of the function. So I'm going to use this. So negative 2x plus 4 squared x minus 1, x minus 2, x minus 6. And I want that to be, remember the graph, I want it where the graph is positive, where the y values are positive. So I'm going to make my inequality greater than 0. And I can't put equal to because, especially because of that negative 4, right? The negative 4, all these values are not part of the solution. So that forces me to just put greater than, not greater than or equal to. Okay. Now, one thing I can do here, remember I said you could either decide to have your graph above or below, and you're looking for negative values. So here's another solution to this, very similar, and it all comes from what if I divided both sides by negative 2, then my secondary inequality would be this. So x minus 1, x minus 2, x minus 6, and since I divided both sides by negative, it changes the sign to become less than 0. So this would be, these would both be valid inequalities, and they both give us the exact same solution as we created, which duplicates the solution in interval notation. Okay, so that's an interesting question. I like to start with the number line, create the solution from the interval notation, and then maybe come up with a possible sketch of a polynomial that would give you this solution, and then create the equation, and then you have to attach the inequality to that function. It could be less than or greater than, depending on what intervals we were actually looking at here. Okay, so that's it for today. We've got a few homework questions for you here, and that's it for inequalities. So hopefully you see the similarities and differences with solving equations. There's quite a bit more to it than we've seen before with equations. Okay, that's it. Have yourselves a great day, and we'll see you on the next lesson.